How many 3-digit numbers, now we're using all digits 0 through 9, can be created? So it's a spaces question, because you have 3 decisions to make. Are there any restrictions?
Without repetition.
Without repetition is kind of a restriction, but it's not like, is there any restrictions on any of our decisions? Is there a decision that we have to do first? No? Like, is this, what number is that? Is it a 3-digit number? No. So there is a restriction on the first digit. The first digit can't be 0. So we write under that we make a little note that that can't be 0. So then if that's a restriction, we have to deal with that first. How many choices do you have? There's 10 digits including the 0. Take out the 0. I had someone this morning double check it by going 1, 2, 3, 4, 5, 6, 7, 8, 9.
That's public.
It was very enjoyable. And now 0 can be put back in, but we're not allowed to repeat. So how many choices do we have for this one? 9 again. Because one of the 10 digits has been used up, but 0 goes back in, so you have 9, and then 8. Multiply these together, 648 total possibilities. Okay, a little mental math to warm up. Simplify all of these. Did you get 42 for the first one? Did you get, ooh. So when simplifying factorials, we start with the biggest one. Of course, 10 is the biggest here. And you go down until you hit one that's on the bottom, which would be 6. Well, that would cancel out with this 6. And then the 4 factorial, if you expanded that, that would be 4 times 3 times 2 times 1. Can you see that 4 times 2 would simplify with the 8? And the 9 and the 3 don't go away completely, but 9 divided by 3 would leave you with 3 on top. And now there's nothing left on the bottom, so that would be all 1s. And on the top you have a 10, a 3, and a 7. That would give you 210. So in simplifying factorials, we always expand the bigger one in order to break it down. The same thing happens when you use variables. So I have an n plus 2 factorial over an n factorial. Which one's bigger? N plus 2. So we'll leave the n factorial on the bottom, and we'll start expanding the top. So n plus 2, what's 1 less than n plus 2? N plus 1, what's 1 less than n plus 1? N. And when you get to n, then you could add the, to say it would keep going, and these would simplify, and we're just left with n plus 2 times n plus 1. And you could multiply that out or leave it factored. Either would be fine. Now we learn about factorials because they're really helpful in permutations. Permutations are where the order is important. And we highlighted this before, so we'll highlight it again. In permutations, the order is important. So if you wanted to write all the permutations of ABC, well, all 3 of those letters are different. You could do 3 spaces for 3 decisions. What letter is going to be first? How many choices do you have? 3, and then 2, and then 1 would be 6 in total. And if we wanted to write them out, it could be ABC, ACB, BAC, BCA, CAB, CBA. And if they're all different, that's where the factorial notation can come in. That's equal to 3 factorial. So this is our permutation formula, saying that if you are arranging 5 objects of 10, then you could write that as 10p5. Although we generally use the spaces for it, but we'll see in some situations it might be nice to use this instead of the spaces, especially if you had lots and lots of spaces to do. So here's some examples of if you have the same number. If I did 6p6, well, that would mean 6 spaces starting with 6. Does that make sense? That would be 6 factorial. Now, when you use the formula ends up getting a 0 factorial on the bottom. Now, 0 factorial doesn't fit the pattern of any other number, but we learned before that by definition, 0 factorial is 1. So that's why this is just equal to 6 factorial over 1, which is 6 factorial. Number of ways a program of 4 pieces of music where the order matters can be made from 10 songs. So in this, if you use the spaces, can you see that you'd have 4 decisions to make? What song are we going to play first? How many choices? 10 songs. So you could choose any one of those 10. How many choices do you have for song number 2? 9, then 8, then 7. And this is the same as 10p4. What's that? Right, because the formula for this would be 10 factorial over 10 minus 4 factorial. And you can, if you expanded that, you might see why it's 10 times 9 times 8 times 7. So this is all review right now. Math. All 4 letters are different. How many permutations would there be? 4 factorial. You could do the spaces if you wanted, right? You have 4 decisions you need to make, 4 choices for your first letter, then 3, then 2, then 1. Yes? Well, that means that this is different than them. Right? If the order didn't matter, like some games, you just, like poker, for example, you get your 5 cards. You can rearrange them in your hand. It doesn't matter the order you got them in. Those are still the 5 cards you're playing with, right? But in English, right, the math and them are 2 different things, right? They don't mean the same thing. Okay, now here's the first question where your brain wants to play tricks on you, because we're normally thinking about decisions as spaces and then putting our choices into our spaces. This one's hard for students because you like to put students into desks. You don't like to put desks into students. And so your brain wants you to draw 12 spaces because you see 12 desks. And you want to put people into desks, because that's what normally happens. But you have to remember that your spaces represent your decisions. And there's only 5 decisions that have to be made. Person number 1 comes into math help, and they say, where am I going to sit? How many choices do they have? 12. And there's a decision for person number 2, a decision for 3, 4, 5. So you're putting the desks into the people rather than the people into the desks. Right? Now, generally in math help, you don't come in and sit on somebody else's lap. So second person comes in, how many choices do they have? 11, then 10, then 9. Right, right. When that does happen, it's a little awkward for a bit. And then and you could do this as 12p5. How many different seating plans? Right now I have 1, 2, 3, 4, 5, 6, 7 rows, 35 desks, and how many people are here? 8, 12, 16, 22 people are here. So 22 decisions would need to be made for a seating plan in here. This is a place where the formula is nice, because we would have 22 decisions and there's 35 desks to choose from. This is a huge number. So if we go to our calculator, You type in 35, hit your math button, and the same place where you have the factorial sign in probability, you have an NPR sign. If you do that, we'll see if this is even possible to calculate. It is 1.65 times 10 to the 30. So if over the weekend I'm like, all right, I'm going to make a new seating plan. In fact, I'm going to write out every possible seating plan for you guys that I can think of. And then you'll just draw one from the hat on Monday to see where you're going to sit. How many would I have to write out? Well, that doesn't really give justice to the numbers, so I'm going to just write out 1, 6, 5, 9, 4. $30. It was e to the 30? Yeah. That would be an approximation. Is that a big number? Yes. So if I got you to guess, if you guessed the seating plan correctly, you get 100% in this unit, I'd be pretty safe to say that none of you would get it right. But it is possible. We're going to change the title of this so that it matches what it was in our textbook. So you can take this out and write identical objects. And we've done these already as well. So this is a little bit of review. What do you do with egg? All the permutations of egg? Well, that would be 3 factorial if all the letters were different. But since we have identical objects, those two G's are the same, we have to divide by 2 factorial. And with Assisipi, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's 9 letters. But there are 3 S's, 2 P's, and 2 I's. So you'd have to divide out those repetitions. So with identical object questions, you've got to be able to figure out when it's an identical object. So you're looking at questions where you have to arrange things, but some of the things that you're arranging are the same as other things that you're arranging. So in this question, contractor is putting houses up on a street. There's 3 of model A, 4 of model B, and 2 of model C. So if you wrote this out, one example could look like that, and you see that you have identical objects. How many ways could they be arranged on a street? Well, normally it'd be 9 factorial if they decided to make all the houses different, but since some are identical, have you driven down streets where they have like 3 different types of houses and they just sort of like, oh, there's that one, and then it doesn't, oh, there's another one of that one. You should have gone out the gate.
I get confused, like when to use the dash, 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 when generally just think, just answer.
Right. So if you've got a question where there's choices and everything has no identical objects, then you're going to use the fundamental counting principle and just do your spaces with choices. For this one, you've got identical objects, so then you're going to use your identical object strategy, which is like the 9 factorial is like the dashes, 9, 8, 7, 6, 5, 4, 3, 2, 1, but then you have to divide out the fact that because they're identical, some of those arrangements are the same. Try this one. So if we draw a picture of this, draw our city blocks. John lives 3 blocks north and 6 blocks east of school. So if here is school, here is John's house. Wow. Now, one possible route that could take him home would look like this. Straight north, straight east. And that would be represented like that. And if you realize that every route that he takes home is just a rearrangement of those norths and those easts, because he always has to go north 3 blocks. He always has to go east 6 blocks, but the order that he does that doesn't matter. Becomes a question of how many ways could you rearrange those letters that are different. Now, if they were all different letters, it would be 9 factorial, but we have identical letters in there. So it becomes 9 factorial over 6 factorial, 3 factorial. Now, the other way that you could count this is counting each intersection and the pathways along the way. For example, here and here, there's only one way to get to those intersections. In fact, all of these ones along here and up here would all be 1. Because the only way that he can get to this intersection, there's one pathway to get there. There's no other ways to get there. Again, assuming he always is walking closer to this point that he wants to get, not backtracking or doing any loops. And then how do we figure out this one? Well, if there's one way to get here and one way to get there, the way that he could get to that intersection is via this one way or via that one way, making 2 ways to get to that one. And there'll be 3 ways to this one and 3 ways to this one. 4, 4, 5, 6, 7. Yes. They might, or they might give you a diagram, because sometimes there's questions where there's like, oh, there's a lake in the middle. Okay, and he doesn't want to walk through the lake, so now how many ways can he get home? But we'll add the lake after. So this will be 6. 4 plus 6, this is 10. 6 plus 4, 10. 10 plus 5, 15. 21, 28, 20, 35, 56, 84. You want to see how you would do it with the lake in there? So if I take away, let's put the lake, like that. Can you see that all those other numbers would stay the same up till now? This will still be 7 here. How many ways can you get to this spot? 10 plus, well, he can't come from here, so that'll be 0. This would still be 10. This one would be 10 plus, well, it stayed 10. This one here would be 6 plus, still 6. This one will be 13, 16. If you put that lake in there, there would be 29 ways that he could get home. The last strategy, again, I'm just going to call it grouping. That's all I'm going to call it. So if you want to just, we'll call it the grouping strategy. Sometimes you want certain things to be grouped together. If that's the case, we have to, first of all, think about how many groups that we have, then think about the permutations within each group. So for example, I have my collection of 4 different calculus books, 5 different algebra books, and 4 different geometry books. Okay? The grouping strategy is sometimes confused with identical objects. That's why I said, in this case, they're different, because it doesn't make sense to have 4 of the same book on your shelf, although some people might do that. Okay, so we're going to say the library. But we're going to say there are 4 different calculus books, 5 different algebra books, and 4 different geometry books. And I want to arrange them on the shelf, but I want to keep the groups together. So first of all, the first decision I need to make is how I'm going to arrange my groups. Should I do algebra, then calculus, then geometry because that's alphabetical? Or alphabetical sucks, I should change it up and maybe, or calculus first because that's my favorite, then algebra, then geometry. So first thing I have to decide is how I'm going to arrange my groups. And since there's 3 groups, there would be 3 factorial ways of arranging the groups, right? Algebra, calculus, geometry, algebra, geometry, calculus. Calculus, algebra, geometry, calculus, geometry, algebra. Geometry, calculus, algebra, geometry, algebra, calculus. And that would be 3 factorial or 6 ways. But then once I've decided I'm going to go with calculus, then algebra, then geometry, well, then I have my next decision is how am I going to arrange my calculus books? Well, I have 4 calculus books. How many ways could I arrange 4 calculus books? 4 factorial. And then my algebra books. 5 factorial. And finally my geometry books. 4 factorial. And we multiply all of these together and it will tell me how many ways I could arrange them all if I kept the groups together. So to recap, going back to the original slide, we first figure out how many groups we have, number of groups factorial, and then we look at each individual group and figure out how many ways we could arrange that group. So there's 5 people. Amy, Bill, Jill, Lee, and Tom. They're sitting on a park bench. And it's springtime, and Jill and Bill wish to sit together. So this is a grouping question because you have 2 people that want to sit together. The other people don't have to sit together, so Jill and Bill, of the 5 people, they could be together on the end, they could be together somewhere in the middle, or they could be together on the other end. How many groups do we have? Well, but you still have to consider all the things that are there. So we start with 5 people, and if I put those 2 together, it's like we have 4 groups. Okay? And sometimes this is even easier to think if you like glue them together. Have you ever seen couples that are sort of like glued together all the time? You can't see one without the other. It's like having 4 people, right? You've got Amy, Lee, Tom, and the Jill Bill, right? Because they're always together. You just name them something new. Have you ever done that? Have you ever heard of that? There was a couple when I went to school that were always together. His name was Derek, her name was Carrie, and we just called them Carrick. Carrick. We just combined their names because they were always together. Okay. So, there is 4 groups. So we start deciding how we're going to arrange the 4 people or the 4 groups, the Tom, the Lee, the Bill, and the Jill Bill. The Tom, the Lee, the Amy, and the Jill Bill. Okay, so it'd be 4 factorial ways to decide that. Then you look at each individual group. Of the 4 groups, only, right, Jill and Bill could decide to hold left hand, right hand, or right hand, left hand on the park bench. So there would be 2 factorial ways of arranging them. All the others, you wouldn't have to put, this would be enough, but if you wanted to, well, Amy is 1 factorial. You can't rearrange her. Or Lee or Tom, they would all be 1s. So we don't have to show that because all multiplying by 1. This is going to be 48 ways where Jill and Bill wish to sit together. Because it could be Jill Bill or Bill Jill, right? Depending on which way they're sitting on the park bench, right? They're together on the end and Jill's on the end, or they're together on the end and Bill's on the end. They could be in the middle, and in the middle it could be Jill on Bill's left or Jill on Bill's right. So that's why there's 2 factorial, because that group could be arranged in 2 ways. Okay, so things spread, and the next week, Jill and Bill are still sitting together, and now Lee and Amy wish to sit together. Poor Tom. Don't worry, Tom gets his revenge in part C. So now, how many groups are there? You had 5, but you got Jill and Bill together, you got Lee and Amy together, and Tom's all by himself. There, for your groups, we have 3 groups, so they could be arranged in 3 factorial. Yeah, you have to practice that, and then it's really hard to go back and forth between this. Okay, anyways. You've got Jill and Bill, 2 factorial. Lee and Amy, 2 factorial. And then Tom, which you don't have to put here because he's just 1 factorial. Okay, there's now 6 times 2 times 2, 24 ways. Bum, 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 bum. Part C. Okay? In part C, we are going to, I'm just going to make part of this go away for now and just talk about it. Something happens, this is Tom's revenge. Lee and Amy, they're on again, off again. They don't need to sit together. But something happened, and Jill and Bill must not sit together here in part C. Okay? So we're not concerned about Lee and Amy. They could be sitting together. They don't have to be. But this is an example of where the not strategy becomes really important. Because it's hard to figure this out. If you just tried to do the spaces, anybody could sit here, right? You'd have 5 choices. But if you chose Jill, then this can't be Bill. But if you didn't choose Jill or Bill, then this could be anybody. And it gets confusing because you don't know what to write in the next space because it's all dependent of what you chose first. So the easier way is to say, well, I'm going to use the not strategy, which is always all minus the bad. Well, all the ways people could sit on the park bench, well, that's easy to figure out. That's just 5 factorial or 120 ways. The bad ways is when Jill and Bill are sitting together. And we figured that out in part A. How many ways did Jill and Bill sit together in part A? 48. So if we take all the ways, 120, and we subtract all the ways that they're sitting together, what we're going to be left with is all the ways that they're not sitting together. And if you tried to count all the ways that they're not sitting together directly, it would be hard. So now we've added our grouping strategy. We've seen the not strategy again, a not strategy built into a grouping strategy. So in some of your questions, you're going to have more than one thing show up. Okay, we're going to leave the last part for later.